Since the beginning of time, humans have been trying to understand our universe.
In some ways, one of the oldest pursuits, we like to think. I mean, the second you look up at the sky and wonder, you're a cosmologist.
That's Daniel Holz. He's a professor of astrophysics here at the University of Chicago.
For a long time, cosmology, well, at the very beginning, it was mostly theory.
Right.
People would kind of look up and wonder, but the data was what you could see with your eyes. So there's been this series of growing awareness of where we are in the universe and how it all fits together. A lot of that has been driven by data.
And Daniel has spent his entire career chasing a very specific piece of data, something that could allow him to answer two of the most mysterious questions humans have wondered since first staring up at the stars. How old is the universe really, and how big is it? And the thing he's been chasing, the thing that could hold the answers, gravitational waves.
The normal way we describe them is as ripples in space-time. Very, very difficult to detect because the effects are very, very small.
From the University of Chicago, this is Big Brains, a podcast about the stories behind the breakthroughs reshaping our world. On this episode, the search for gravitational waves in the age of the universe. I'm your host, Paul Rand. What happened on September 14th in 2015?
Okay, so that was the date that we detected with LIGO. So it's the Laser Interferometer Gravitational Wave Observatory.
Okay.
And there are two of them.
Right.
There's one in Hanford, Washington, and one in Livingston, Louisiana. So we built a gravitational wave detector. And essentially 2 days before that date, we turned on our detector and we started to listen to the universe in gravitational waves, which is something we'd never been able to do before, certainly at that level of sensitivity. So we turned them on, and then on that date, we, for the very first time, heard something, and it was very loud. I use the term hearing. We're really detecting ripples in space-time.
Okay.
So you're not hearing it with your ears. It's causing vibrations, mirrors to move back and forth. But the signal, if you take that signal and you just run it into your speakers, it's in the human auditory band. And it was just what we call a chirp, a whoop, just that, very short, less than a second long, in both detectors. We analyzed what that was, and we figured out that that was coming from two black holes 1 billion light years away. Those two black holes were orbiting each other and then crashing into each other.
And what did that tell you?
It was the first time we directly confirmed and detected gravitational waves. We had lots of indirect evidence that they existed, but this was the first time on Earth we noticed the passage of gravitational waves.
Okay. If we go back maybe to Einstein days, did he call them gravitational waves?
So Einstein really was the first to recognize that there would be these waves.
Okay.
Einstein's insight was that space and time are not separate entities, but they're linked, which means you can't just look at space separately. You have to really consider it as, in his language, kind of a geometric fabric. It also was the first time we probed sort of the nature of black holes up close and personal. So we were really hearing what happens when black holes go around each other. They kind of stretch and bend space and time. It's very extreme. These black holes ended up essentially crashing into each other at over half the speed of light. So it's a very extreme physical scenario, and everything that happened agreed with what Einstein said should happen, and we could, confirm that to pretty high precision.
What was it like being in the room during that moment?
Yeah, that was really a kind of insane experience.
I mean,
that I remember just that whole day when we had the detection. It was so loud and perfect that, to be honest, most of us thought it wasn't real. We test ourselves. We kind of put things into the data stream just to make sure that everything works. It keeps us honest. So someone will secretly put in something, and then we'd better see it. And then when we do see it, we can test whether we infer the right thing. This thing was so loud and perfect in both detectors that everyone just thought, obviously, someone put it in. It was a test. We quickly came to the conclusion it wasn't a test. And I remember even that first day in the afternoon, I sent an email to the collaboration starting to estimate some of the astrophysical consequences. If we've really detected this and it's, it happened this early, this is how often it might happen in the future, and this is what it teaches us about the universe. even that first day. But then we spent 5 months poring over the data, checking and double checking, triple checking, because we knew this was, never been done before. It is a pretty big claim if you're saying we've detected these two black holes in a way that's never been done before, for the first time after 100 years, people looking and predicting. You just don't want to be wrong. So it took us 5 months to be sure we were right.
It's hard to imagine that it almost didn't happen because you were working to get funding for LIGO.
Yeah. In fact, for many years, many prominent physicists, and I think reasonably so, said this is impossible. There's no point in even building this. It's never going to work. And that's because the level of precision you need to measure these gravitational waves is astounding. So LIGO is by far the most sensitive instrument that's ever been built. And it took decades, and it took, when it was first proposed, it wasn't clear that the technology would get to the point where we could actually build this. It is amazing that everything really did fall into place and that it works. It was not a given. So I think this is one of these cases where it was funded by the National Science Foundation. So it's taxpayer dollars, and it was a big risk, and it was very contentious. And the reason they did it was because it was, in some sense, true blue sky research. Like, we would learn to be able to have this whole new way to learn about the universe. It's so exciting. The potential is so high that it's worth the risk. And they made that decision, and it took a few very brave souls along the way to push that forward. And it's been, richly rewarded.
If you're listening to Big Brains, there's a good chance you consider yourself a lifelong learner. However, you may not know about the University of Chicago's Graham School and its focus on continuing liberal and professional studies. For more than a century, Graham has been a destination for lifelong learners. They offer courses online and in the classroom, bringing the transformative education UChicago is known for to students of all ages. To learn more about the courses, certificates, and degrees, visit graham.uchicago.edu. So many scientists go through their entire careers waiting for one discovery of this magnitude. But 2 years later, something also really meaningful happened. Can you talk about that?
So after the binary black hole, that was a pretty, exciting discovery. It had a lot of impact. What we've been waiting for, what I've been personally most excited about, is a binary neutron star. And the reason for that is black holes are black and no light comes out of them. So when you take two black holes and you collide them, you don't get any light. They're completely dark. Now, that's fine. They're very loud in gravitational waves. We detect the gravitational waves. That's great. But it would be fun to also see light. And if we could do that, then that allows us to learn even more about the universe. And so that's sort of been a holy grail of the field. It's something we call multi-messenger gravitational wave astronomy. It's when you get gravity and light at the same time. In August 2017, I was actually giving lectures in Hong Kong talking about this. If only at some point we would detect gravity and light, gravitational waves and light waves from the same object, well, then we could learn all these additional things about the universe. That would be fantastic. It's something we kind of hope will happen at some point. A lot of things would have to go right. We've never even, the most obvious source would be two neutron stars, but we've never detected two neutron stars in gravitational waves, and then would have to be lucky enough to point the telescopes at them fast enough to catch the light. If there is any light, we don't know. It's all unknown. That's the way science works. It's all unknown. So I'd given this series of lectures, and then I got on a plane and I was flying back to Chicago. When I landed, my phone basically blew up. Like, I turned it on, and you know how usually you get one
all
beep.
the pings.
It just was relentless. It was actually embarrassing. Everyone around me was like, what's wrong with your phone? And it was because we'd had a detection. A few hours before I landed, there'd been this detection, and it looked like two neutron stars. That was this thing we'd been waiting for. That was it. The question was, would there be any light? I got off the plane, and I walked off the plane holding my laptop, and I was doing analysis as I was walking off the plane, got home, walked straight into a bedroom, closed the door, like, hi kids, straight into the bedroom, and that was it. And I was gone for the next at least the next day, like just had no time for anyone because immediately, because we'd had these binary neutron stars, the goal was to point telescopes. Mm-hmm. And I had been part of a group where we had co-opted a telescope in Chile, the dark energy camera, which is used for the dark energy survey, which Chicago plays a major role in. We then had to figure out where to point the telescope and how to make it all work. There were some people that were supposed to be using the telescope that night. We booted them off and we arranged everything. And meanwhile, we had to get the maps to know exactly where to point from the LIGO collaborator. There was a lot of work to do. And we managed to pull it all together somehow and point our telescope and find the new star.
My gosh. And
just the detection of the binary neutron stars was this sort of watershed event, as you said. I mean, first there was the binary black hole. That was a great, great moment. This was an even better moment for me because it's something I'd really wanted to be able to do. And then less than 12 hours later, we saw the star associated with it, which was, I mean, I can't even tell you how amazing it was to have that all fall into place.
Part of what you're getting to is trying to get an understanding through this type of a measurement about how fast the universe is expanding.
So the Hubble constant is the measure of how fast the universe is expanding around us.
Okay.
And when you look at galaxies, you'll notice that the galaxies are receding from us. And the farther away they are, the faster they're receding from us. And if you think about that, that picture is a universe that's expanding all around us. And the rate at which it's expanding is related to the age of the universe and the size of the universe and a lot of other properties, what the universe is made out of, what the future evolution of the universe might be. All these questions are related to what's it doing around us right now.
Okay.
It's been something we've been trying to measure for a long time. Edwin Hubble was the first person to measure.
Also from the University of Chicago.
Also from the University of Chicago. And his measurement was actually quite high in the sense that now we think the measurement's around 70 and his measurement was a few hundred. And that caused some paradoxes at the time because it implied that maybe the age of the universe was less than the age of the Earth. And so this has been one of these things we've been trying to pursue for quite a while, really nail down this number. In part just because it'd be nice to really know the age of the universe. It seems like just kind of a cool thing to accurately measure, but also because it relates to things such as what the nature is of dark matter and dark energy and other big mysteries. And then because I had the star and I could figure out sort of what galaxy it had come from, and because I had the gravitational wave data, I could do this measurement of distance and the velocity with which the galaxy was receding, and I could directly measure the Hubble constant. And so this sort of measurement, which I'd been talking about for many, many years, and which for me was sort of the goal of my career, I then just did it. I could just calculate. I did it that evening. Like, here's the number. It's all done.
Wow.
It was, that was quite an experience.
And there's a little controversy in here. Is that right?
Yeah. We have different ways to measure this number, this Hubble constant, and we're getting different values, and the values don't agree. One is 67, one is about 72, but they're measuring the same thing, just in different ways. And they should agree, and they don't, and we don't know why. We've come up through gravitational waves with a new way to measure this number, and it's a very elegant and simple way to measure it. It's not based on black holes. It's based on neutron stars and measuring the gravitational waves from neutron stars and then also seeing light from the neutron stars. And when you do that, you just get a direct measurement of this number that in effect, the gravitational waves, how loud the gravitational waves are, tell you how far away they are, the sources.
And the reason it's controversial, why is that?
So we'll have this new way to measure things. We've done this first measurement. We did it with this binary neutron star event in, I guess, last year, 2017 in the fall. And we got a measurement which was right in between these two other measurements, but with large uncertainties. As time goes on, we're going to get, and that's what, this was a paper I wrote, and I should say this paper was written with Xinyu Chen, who was a former student here at UChicago. She's now at Harvard, and Maya Fischbach, who's a current student here at Chicago. So the three of us wrote this paper, and what we pointed out was that as we get more and more of these binary neutron star sources, we're going to measure this value of the Hubble constant very accurately. And depending on where it falls, we might confirm one method or the other method, or it could fall somewhere completely different. No matter where it falls, it's going to be interesting.
Capitalism is the engine of prosperity.
Actually, it sows the seeds of its own demise.
Could both be right? I'm Kate Waldock from Georgetown University.
And I'm Luigi Zingales from the University of Chicago.
We're the hosts of Capital Isn't, a podcast about what's working in capitalism today.
And most importantly, what isn't.
We're going to share the sort of irreverent banter you'd hear between economists at a bar.
That is, if economists were to go to a bar.
Subscribe to Capital Isn't. You can find us wherever you get your podcasts.
The speed of discovery has really picked up quite a bit. And so if you're looking at some of the students coming in saying you have no idea how exciting it is to be where you are right now.
It's been fantastic. I mean, our understanding of the universe, where we are now compared to where we were even back then when I first set foot on campus, it's really increased by leaps and bounds. And there's no indication that this is going to slow down.
What got you going down this path?
Yeah, I think it's probably a common story, which is I was always somewhat interested in physics and math. But then in college, there was this one professor that I started working with, and he was remarkable. This was John Wheeler, and he's sort of a legend within the general relativity community, just full of life and so excited about the science. Mm-hmm. And it was absolutely infectious.
He passed it on.
He passed it on. So I remember walking into his office and saying, I'm just kind of interested in this stuff, and I'd love to work on a project if you have any projects. And I remember this day very clearly. He immediately sat me down and said, well, here's a project you might be interested in. And it had to do, as it happens, with gravitational waves and black holes. And he kind of laid it out. And that was the next year and a half of my life, was every day I would go to his office, and he'd always start the same way. What's new? What interesting thing do you have to tell me this morning?
And so you tried to have something.
I had to. So I was up very late almost every night preparing so that I would have something interesting to say. And at first, looking back, I didn't have anything. I mean, I was just a kid. I was learning, but by the end, we had really come up with some interesting results. And once you have that experience of really figuring out something new, you're hooked. And so that was it. And so he said, well, if you want to continue, you have to go to UChicago. Here's the path.
Okay.
And so here I am.
That's remarkable. As you think about your own aspirations for what you want to continue learning and evolving, where is your energy focused?
Well, so right now, I'm still very focused on this gravitational wave work. It's something I've spent a good part of my career thinking about and trying to anticipate, and talking about, if we were to ever measure gravitational waves from, say, neutron stars, that would be so amazing because we could do all this interesting science. And that was, I wrote lots of papers saying, if only we could do that, then we would learn these other things. And it's been remarkable because just in the last few years,
because it's not if only anymore.
Now I removed the if only. We have this data,
right?
And look, here are some things we've learned.
Oh my gosh!
And that's been a really, really fun transition. But it's just the very beginning.
Right.
We have no idea what we're going to hear next. And as we get more sensitive, maybe we'll hear some things that are really surprising. We expect to just get more and more, where more and more is instead of, on the order of 10, we'll be talking about hundreds. Maybe we get one of these every week or maybe even more. We're just going to be inundated. And so now there's really this shift. Instead of lovingly analyzing each one, the question is now we'll have just so many. What do those as a population teach us about the universe?
Let me ask you one final question. You joined the Bulletin of Atomic Scientists, I guess, last year. Is that right?
Yeah.
When I think of, for lack of a better word, existential threats to society is what I think of with that group. How does what you do fit into that?
This has been something I've been thinking about a lot. Now, it's not that, a black hole is going to come and swallow us up and therefore we should worry about it. And that's why I should be part of the bulletin, because I can help estimate whether that's going to happen or not. It's very unlikely to happen. We don't have to lose sleep over that. I think there are two parts of my association with the Bulletin. One is that the Bulletin was founded by scientists, including many scientists here at the Enrico Fermi Institute and associated with the university. And there's a history of scientists and physicists in particular being engaged in questions that have impact on society. And this sort of thing of, global annihilation is clearly something that has impact on society, and it makes sense to be engaged on that. So that there's kind of a history of that. But, for me personally, it's something I think about a lot and I worry about. And it's something I feel like it's sort of the most important, challenge facing us today. I mean, I would really want to know what the Hubble constant is, but being aware that, climate change or nuclear annihilation is on the horizon, it's something we really need to think about and try to address. That's far more important in some ways. And if I can help build that awareness and, somehow move us away from this brink, I feel like I have to do my part. This organization, I think, is one of the most effective organizations at really trying to understand the risks, trying to assess those risks and communicate them.
Right. Well, what I gather from this conversation and seeing other things you've done is you do a really wonderful job explaining this. Do you enjoy doing that level of education?
Yeah, I don't know how effective I am, but it's really fun. And it's really, the trick with this stuff, it really is amazing that we've been able to do any of this and that the universe has been so kind as to provide these incredibly loud sources for us to detect. And the whole thing has just been, quite remarkable. So I feel very lucky, and I try to get that across.
You do a wonderful job at it. And it's been just an absolute treat having you on Big Brains today. Thanks for being with us.
Yeah, thanks for having me.
Okay.
Big Brains is a production of the UChicago Podcast Network. To learn more, visit us at news.uchicago.edu and subscribe on iTunes, Stitcher, Google Play, and wherever else you get your podcasts. Thanks for listening.